Okay, let's go over section 11.4, but first, let me show you one thing that I didn't talk about in section 11.3. Finding the domain of a log function, a logarithmic function. So suppose we're supposed to find the domain of f of x equals log base 8 of 4 minus 5x. Now the domain of a log function, if we had some function y equals log base a of x, that x must be greater than 0. Remember, the domain is from negative infinity, I'm sorry, from 0 to infinity. That's a domain. You can't take the log of a negative number. You can't take the log of 0. So every time if you're asked to find the domain, or you want to find the domain of a log function, excuse me, whatever the argument is, you got to make sure that's positive. So to find the domain, all you do is take the argument of the log function, the 4 minus 5x, set it, make it greater than or equal to 0. Solve this inequality. 4 minus 5x is greater than 0. So subtract 4 from both sides. You get negative 5x is greater than negative 4. Divide by negative 5, which, remember, when you multiply or divide both sides by a negative number, the order changes. You switch this inequality symbol around. Now it's a less than. So I divided both sides by negative 5, and I get x on the left side, 4/5 on the right side with a less than sign. So x is less than 4/5. That's the domain. So the domain is from negative infinity to 4/5 in interval notation, or you can just write that, or you can write it in set Biddle notation like this. It's a set of all x such that x is less than 4/5. Okay, but that's what you always do. If you have, some function g of x, and it's log whatever base it is, as long as that base is greater than 0 and not equal to 1, that's what a has to be. Whatever is here, question mark, just set that question mark greater than 0 and solve this, and you get the domain. Okay, 11.4 is entitled Properties of Logarithms. Now they go through a whole bunch of properties that we already talked about, so here they are right here. Notice this one right here, log base a of 8 of the x is x. I showed you this one over and over and over again. So if you know this one, you really don't need these two, because look, log base a of a to the 0th, if you put a 0 for the x, this is 1. So this is equal to log base a of 1. And remember, when these two, when these are the same number here, this base and this base, you get the exponent back. This is a composition of inverse functions. So when we have this, we just get 0. But and I also told you, log of whatever the base is, as long as it's an appropriate base, if there's a 1 here, if you're plugging 1 in, you get 0 back. 1, 0 is always an ordered pair of log base a to just x, or just one letter. I told you can move those graphs around and stuff, but we're not doing that. If you put a 1 where the x is, see, this would be a 1. The answer is 1. So really, you just need to know this one, and then these two are special cases of that one. And we also went over this one. A to log base a of x is x. When these two bases are the same again, you get this. It's a composition of inverse functions. They're undoing each other. Remember, a log, like this right here, this is the exponent you put on a to get a to the x. I kept saying that over and over again last video. So if this is the exponent you put on a to get a to the x, clearly you put an x as an exponent on a to get a to the x. So that's the answer. This one, look, this is the exponent you put on a to get x. If you put it on a, you get x. I went over and over that again, that in the last video. And then there's a whole bunch of examples in 11.4, or maybe not a whole bunch, but there's examples showing this. But, if you had 12 to the log base 7 of 12, if you have 12 to the log base 12 of 7, see if these two numbers are the same, 7. That's this one. See, that exponent there, that's the exponent you put on 12 to get 7. So you put it on 12, you get 7. If you had log base 0.7, let's say of 0.7, say you just had that. Oh, look, this is like 0.7 to the first power. So you get 1. That's just like putting a 0.7 here and a 0.7 here. What exponent do you put on 0.7 to get 0.7 to the first power? 1. If this was squared, you get a 2, etc. But we went over that kind of stuff. Okay. All right, some other properties of logarithms. Suppose we let x equal log base a of m. That's equivalent to writing this in exponential form to a to the x equals m. Now, we went over that over and over again, so you should understand that. That's where m and n and a are all positive, and a can equal 1. Remember, that's how we restricted it. And let's let y equal log base a of n. Now, the equivalent exponential form, a to the y equals n. And again, the m, the n, the a are all positive, and the a can't be 1 based on, the restrictions we talked about before. And you can't take a log of a negative or 0. That's why m and n have to be greater than 0 also. Then, understand, letting x equal the log base a of m and y equal log base a of n. Then, log base a of two numbers, m times n, remember m and n are both positive, equals, now since I called, I let x equal log base a of m, then m is a to the x. So I put a to the x in there, I just substituted it in. And since I let y equal log base a of n, then n equals a to the y. So in place of that n, I put a to the y. So log base a of m times n becomes log base a of a to the x times a to the y. And by properties of exponents, we know already that we can write this with one base and add the exponents together. See, the bases are the same. So a to the x times a to the y is a to the x plus y. So now we have log base a of a to the x plus y. These two a's are the same. Or you can think of this as the exponent we put on a to get a to the x plus y. But this is a composition of inverse functions like I just spoke about a minute ago, and we're going to get the exponent back. See, that's just equal to x plus y. And since x equals log base a of m, and y equals log base a of n, we can substitute those back in. So look what we have. Log base a of m times n equals the sum of log base a of m and a log base a of n. So when you have a log of a product like this, log base a of m times n, you can write it as, using this property, equals log base a of one factor, m, plus log base a of the other factor, n. And you can change the left side of this equation into the right side, or you can change the right side into the left side, as long as m, n are both positive, and a has to be greater than 0, not equal to 1. This is called the product rule for logs, or of logs. What was I going to say? I don't remember. Okay. So here's the product rule of logs. We just derived it. Now, in a similar fashion, you can derive the quotient. And by the, I know what I was going to say. Here's what students do sometimes. This is just a caveat, a warning. See, I see this kind of stuff. This is the kind of mistakes I see. Oh, this is equal to log base a of m times log base a of n. That is wrong. Don't do that. The log of a product is not the product of logs. Not true. This is the rule. So you got to remember them exactly. So here's the product rule again. There's also a quotient rule for logs and a power rule of logs. Here they are. I'm not going to drive them, but prove them, but you can do it in a similar fashion to the way I did the product rule. The log base a of a quotient, m over n, equals the log of the numerator minus the log of the denominator. That's, again, where m and n and a are all positive and a can't equal 1. That's because the base has to be greater than 0, not equal to 1, and you can't take the log of negative numbers or 0. Again, a warning. If I have the log of m over n, sometimes students write this, log base a of m over log base a of n. Wrong. Don't do that. That is not true. Memorize it exactly the way it is. Here's the power rule. If you have log base a of m to the kth power, you can bring this k down here in front and multiply it by the log base a of a. Again, with those, m has to be greater than 0, a has to be greater than 0 and not equal to 1. Okay? All right, so you should know these properties. You should memorize them. I mean, especially if you're going to take more math, obviously, but memorize them, all these. A comment also. This works for ln then also. Say we had ln of x squared. Well, by the power rule, we can bring the exponent down and write it as 2 times ln of x. Problem, we're not going to worry about this, but these are not always equal. Look, this side, for that side, you can use any real number you want long as x is in 0. You can put in positive numbers or negative numbers because you're squaring them. But this side, you can only put in x is greater than 0. So you got to be careful when you use these a little bit because, it's just one example. So you graph, if we graph 2 times, ln of x looks like this. 2 times ln of x just stretches it away from the x-axis. So this is what y equals 2 times ln of x would look like, that graph. This graph actually looks like this. It actually has a part on this side and a part on this side. So that's that graph. It has both of them. But anyway, don't worry about it, but just a little warning. Okay, so those are a bunch of properties. Now, how do you use them? Let's try a couple things here. Let me see. Get a piece of paper. Okay, so now we have these properties. Let's see. Bunch of examples in the book, but let's use some of them. So, and how do they word it? Like if I had log whatever base, that's just, if I don't put a base, let's say I don't put anything here, just to say, I'll leave it off so it's a 10. Say we had 4 times 7, for example. Well, by this product rule, I could write this as log of 4 plus log of 7. And if I wanted to, this one, it's a log of 2 squared plus the log of 7. This one, I could bring the 2 down over here and write it as 2 times log of 2 plus log of 7. Now, usually the directions, which I didn't write here, you can look at them in a book, but it might say, simplify each using these properties, or write it as a sum of logs, and maybe write it as, bring the exponents down. I don't know how they word it in the book. Let me look at one. Sometimes they just say expand the log too, but write the log as the sum or difference of logs. Here's the sum of logs. What else? Use the power rule to do it, or whatever. But I mean, if you're told to expand the log, you write it out like this. Now you should be able to go backwards also. You should be able to condense it into one logarithm. Write this as a single logarithm. You could go backwards. Move the 2 up here using the power rule. Then it would look like this. That's a 4. So then you could, write it like this, because that's a 4, and then use the product rule to go kind of backwards and write it like that. So you should be able to go both ways. Suppose we had something like this. Say ln of, let's just make something up here. Let's say we had Well, there has to be a restriction anyway, so it doesn't matter whether I put a 5 or 4, but let's make that a 5. Suppose you were told to expand this log. Expand that log. In other words, write this as a sum difference, as a, these constants times logs, bring down the exponents, in other words, expand it using these properties. Change it to like the stuff on the right side. So let's see how we could do that. This is kind of a complicated one, but watch. So you see it's a quotient. Now you can do it different ways depending on how you express this. But, you'll get the idea. So I'm going to use the quotient rule first of all because that looks like a quotient. So the quotient rule says take the log of the numerator minus the log of the denominator. So I could write this as ln of x squared times the cube root of 2x minus 5. Now, I'm going to switch that right now to 2x minus 5 to the 1/3 power because I'm going to use the power rule eventually. So I'm going to write that as 2x minus, here I don't have room here, let me move down here. So equals ln of the numerator, x squared, times 2x minus 5 to the 1/3 power, writing it with an exponent, like that, minus the log of the denominator, ln of x plus 7 to the 3/5. Follow? I'm just using this rule. Here's a product. So let me write this one as ln of x squared plus, using this product rule here. Since it's a product, I'm going to write it as a sum of two logs. ln of 2x minus 5 to the, this is 1/3, not 1/2. I wrote 1/3. 1/3. My fault. So change it. Minus, let's go ahead and bring the 3/5 down right now using the power rule. So let's pull that 3/5 down. Now let's pull down these two exponents using the power rule. So I can write this one as 2 times ln of x, bringing the 2 down in front, plus, bring down to 1/3, 1/3 times ln of 2x minus 5, minus 3/5 times ln of x plus 7. So if you were told to expand this and you knew you were supposed to use these properties, which is what it means, you'd write it like this. Don't stop here. Write it out like this. And then you used, I don't know if you can see all that, but everybody see what I did? I mean, can you tell? So I think it fits on the screen there. I'm trying to make it as big as possible so you can see it. But, use the quotient rule, log of the numerator with the log of the denominator. Here's a product. Use the product rule. Write it as a sum of two logs. Log of each factor added together. Minus, you can bring the 3/5 down now. You can wait and do it at the end. Then use the power rule again to bring the 2 down in front of here and the 1/3 down in front of this log and multiply. And there it is, totally expanded. Okay? Now you should be able to go backwards also. If it says, if it said write, that as a single logarithm. I'll just write log, but write it as a single logarithm or condense it. You should be able to go backwards. You can take this 2, move it back up here. Take this 1/3, move it back up there. And if you want to, you can take this 3/5 and move it back up here right now, or you can wait. But I could have, since I'm doing that, I might as well move the 3/5 up there right in that step. Okay? Those two are added together, so I could write it as a product, like this, using the product rule. Then there's a minus sign, so let me, I used the product rule. See, it looked like this. It was 2 of them added together with the same base. So I wrote it as one log. Now the bases all have to be the same. They're all base E here, but they have to be the same to do this. So now I have this step, combining these two. Log of a sum of logs is log of a product. And because of that minus sign, now I can say it's one log with that as the numerator over the x plus 7 to the 3/5. And I'm right back to the original one. So you should be able to go both ways. But that's an example. I hope that helped you understand that. Okay? All right. Okay. That was an example of what? Oh, yeah, that's okay. All right. Now, also, as I showed you in the last video, on a calculator, we have an ln button. That means you're taking the natural log base e, and we have log, which is base 10 log, the common logarithm. We don't have any other ones. We don't have log base 3 or log base 1/2. So how do you find something, like log base 5 of 15 or something like that? How do you find that? Now, log base 5 of 15 is an irrational number, so that's the exact answer. But how would you, for example, find, log base 5 of, let's even say 12, for example? Here's the exact answer. How do you approximate it? How can you write it in decimal form, at least to as many decimal places as your calculator goes? By the way, we can ballpark this. Notice, here, let me write it over here on the side maybe. Notice log base 5 of 5 is 1, because that's log base 5 of 5 to the first power. This is the exponent you put on 5 to get 5, 1. Log base 5 of 5 squared is 2. You should know why now. See, these bases are the same. That's a composition of inverse functions. It's what exponent you put on 5 to get 5 squared. It's 2. That's 25. So I know the log base 5 of 5 is 1. The log base 5 of 25 is 2. This one's 1. That one's 1. This one's 2. 12 is between 5 and 25. So log base 5 of 12, and log base 5, notice it's base 5. And if you remember I don't have it right here, but the two graphs for log functions, if a is between 0 and 1, remember it looked like this. It was a decreasing function. That's for a between 0 and 1. A log function looks like that. If a is greater than 1, it looks like this. It's an increasing function. That means the bigger number you plug in, the bigger answer. So I know this is smaller than this, and this is bigger. You can clearly tell that by the answers. But log base 5 of 12 would be between those two. So the answer to this, all I know right now is between 1 and 2. Okay? How could I actually get a better approximation of this? This is the exact answer, like I told you. But in decimal form, it's an irrational number. We can't write it exactly in decimal form, but we can approximate it. So I'm going to show you how to use your calculator to do that. But first, we have to develop some kind of formula. So suppose I wanted to find a way to change log base a of something, m, into an expression that has a log b in it. So I want to change this log base a of m into an expression that somehow has log b in it, but it's equal to the same thing. So let's start with this. Log base a of m, let's call it y. Let's write this in exponential form. So a to the y equals m. Now, using some of those properties we talked about. Oh, and by the way, this is true. Now, it's somewhere in the book, but I don't know if I gave this to you yet. But if I have the log base a of, let's say, g, and if that equals the log base a of, let's say, k, then that's true. And the a has to be greater than 0, not equal to 1 again, and g and k both must be positive. I'm not going to write that down right now. But as long as everything's okay, then this means that g has to equal k. Because remember, logs are one-to-one functions. For every x, there's one y. For every y, there's one x. For every domain value, there's one range value. For every range, there's one domain. So if these two are equal, I must have plugged the same thing in. Because there's only, because the y coordinates are equal then. If the y coordinates are equal, there's not two different ordered pairs with, with the same y coordinate, like -2, 4, and 2, 4. That doesn't happen. So g and k have to equal each other. And also, if g and k equal each other, then the log of g equals the log of k, as long as it's a good base and g and k are positive. But that's true. And I don't know why I told you that right there, but anyway, I was thinking I'd need it, but I don't. Let's go back to this. Anyway, you got that now, okay? So, again, I want to come up with an expression I want a way of writing log base A of m using a base B log. So let log base A of m equal y. Oh, I know why I did that, because these two are equal. So I can take the log of both of them, the log of both of them, and they're equal, because what I just showed you. If log base A of g equals log base A of k, then g equals k. Or conversely, if g equals k, then the log of g equals the log of k, same base. So since these two are equal, I can take the log base b of both sides. So log base b of this side equals the log base b of that side. Then I can use the properties of logs, like power rule, bring the y down here. Then divide both sides by log base b of a. Divide this side by log base b of a, so it's gone. And divide this side by log base b of a. So we get y equals log base b of m over log base b of a. This is the change of base law, or formula. So here it is. The change of base formula is log base a of m. Now the y, remember, was log base a of m, so I substituted it back in. So log base a of m equals log base b of m over log base b of a. It's really easy to kind of memorize. Look, notice the m is kind of higher up than the a. So put an m up in the numerator, put an a down in the denominator, and just write the same log in front of both of them. Use any base you want, as long as the base is bigger than 0 and not equal to 1. Okay? So for example, if I want the log base 5 of 12, or I want to write it with a different base. Now, if I want to approximate it, I got to do it base E or base 10, because those are on my calculator. But I can write it in any base I want. Look, I could write it log base 0.05 over log base 0.05. I can use a 0.05 base in both the numerator and denominator. Now, what do I put up here? The 12. What do I put down here? The 5. Log, you see, 12 up here, 5 down here, and write any log you want here with any base. That's equal to that. So is log base 50 of 12 over log base 50 of 12. They're all equal. I can write it any way I want, as long as these, I put a 12 there and a 5 there, and in front of them I write a log with an appropriate base. This number must be bigger than 0 and not equal to 1. So, Now, if I want to actually get an approximation of this, since I only have base E and base 10 on my calculator, I would do one of these, and they're both the same. I'll show you. I would write it either as ln of 12 over ln of 5. See, ln of the 12 over ln of the 5. That's equal to that. Or, also my calculator is log base 10, so I could just write as log of 12. Remember, that's a common log. Common log of 12, base 10 in other words, over common log of 5. Let me show you I get the same answer for both of those. So I'm going to do first ln of 12 over ln of 5. So let's see, ln of 12 divided by ln, oops, I don't know why I keep doing that, but whoops, I just cleared the whole thing. Let me start again. ln of, what was it, 12 over 5. ln of 12 divided by ln of 5. Enter. I get 1.5439, so about 1.54. So this thing equals about 1.54. I just entered this one in the calculator, and that's what I approximately got. So this one's equal to that, so is that one, so is this one. I'm going to punch this one in to show you you also get that. So let's use log this time. So this time I'll hit the log button. log of 12, close the parentheses, divided by log of 5, close the parentheses, enter. Notice I get the same answer, 1.5439. So this one's also equal to 1.54 approximately. These are approximations. Remember, this is actually an irrational number, and you can only approximate it in decimal form because the decimal part goes on forever, never terminates, never repeats. But that's a change of base formula or law, and you should know it and how to use it. But you can change from one base to any other base you want. By the way, let me even show you this. Say I had here. I can change. It's okay to so there's a way of change the base. For something, I'll just put that for something. For something, I'll just put an S in exponential form. I don't want to write the whole thing out. For something in exponential form, some expression in exponential form. Say you had 7 to the 5th power. And I want to write this as 3 to a power. I can do that. Remember this. A to the log base A of x equals x. So if I just put, if I want to change this to with a base of 3, remember this now. So I can write it as 3 to the log base 3 of something. See, these two undo each other. Whatever I put right there is the answer. These undo each other, just like these do. I get that. So if I put 7 to the 5th there, that's the same thing as that. Then I can use those properties of logs, if I want, and bring the 5 down there. And write this as 3 with an exponent of 5 times log base 3 of 7. And then if I wanted to, I could punch this in